Okay. All right. So welcome to the last talk of today. I'm delighted to introduce my former student. Have you graduated yet? William Kretschmer. This summer, in any case, at some point. He's graduating and actually doing a postdoc here at Simons. And he's going to talk about joint work, actually, with three of our other students in our group at UT Austin on learning beyond stabilizer states.
All right, well, thanks for the introduction. My understanding is that we originally had a different speaker scheduled for today, and they were not able to make it, and I was asked to fill in. And I agreed on the condition that I didn't actually have to talk about quantum gravity on the quantum gravity day. So instead, you'll hear me talking about, as Scott said, learning beyond stabilizer states, which is based on joint work with three wonderful co-authors, Sabee Grewal, Vishnu Iyer, and Daniel Liang, who all contributed equally to these papers. The material I'll be talking about is currently split across, I guess, 3 different papers on arXiv and possibly more to come. So with that, I'll get started. And so what this talk is about, a fundamental topic of study in quantum information is understanding how much we can learn from a quantum state. Or put another way, just one of the central questions we try to understand is how hard is it to learn a quantum state? And I do not have enough time in this talk to survey the entire field of quantum learning theory, much less do so in a single slide, but I at least want to give you a few of the highlights, starting with the fact that in some sense, we know the answer to this question is really hard. In particular, if you have an unknown n-qubit quantum state, even if it's a pure state and you want to do full tomography on the state, which just means that you want to learn a complete description of the state that lets you accurately predict any possible future measurement of that state, then you need an exponential number of samples in the system size. And kind of the main place that this has diverted attention to in quantum learning theory is trying to understand when this exponential scaling can be avoided. And there are, in my view, basically 2 approaches to this problem that have gotten a lot of focus in the recent years. The first approach is to just relax what it means to learn this state. So rather than trying to learn a complete description of the state as you do in full tomography, you, for example, maybe just try to predict the state's behavior on some restricted set of measurements, like you might do in the shadow tomography or pack learning models for quantum states. And there have been a lot of success stories in recent years on vastly reducing the sample complexity needed for these kinds of learnings compared to full tomography. But unfortunately, except in some very restricted settings, even these learning tasks still often remain very computationally inefficient, even if the sample complexity, the number of copies of the state that you need, is low. And pretty much the only hope that leaves for getting truly efficient quantum learning algorithms is to look at more restricted classes of states. And there's actually been quite a few developments in really just the last few years, showing that a wide range of highly non-trivial and expressive classes of quantum states actually admit efficient learning algorithms, including things like low-degree quantum phase states, matrix product states, free fermion states, or what will be the focus of this talk, the set of stabilizer states. And to briefly summarize what this talk is going to be about and what we achieve in these works, we give a variety of new learning algorithms for classes of quantum states that generalize the set of stabilizer states. And the common thread in these algorithms is that in each of these algorithms, the runtime, the complexity of the learning scales with some measure of the amount of non-stabilizerness in the state. And of course, in the next few slides, I'll explain to you what I really mean by non-stabilizerness, but this is kind of the high-level intuition. And to really dive into what this talk is going to be about, I do want to at least review, hopefully for many of you, the basics of the stabilizer formalism. And probably the best place to start is by defining the Clifford group, which is the, well, it's perhaps the single most important subgroup of the unitary group in quantum information. It is the group of unitary transformations that is generated by these three gates, the Hadamard gate, the phase gate, and the C0 gate. And this gate set has a lot of nice properties. First off, you'll notice that this the set of gates is capable of generating quantum superpositions, complex phases, and in particular interference, and also entanglement between quantum subsystems, which are three of the essential features of quantum computation that can give it advantages over classical algorithms. But of course, nevertheless, we know that this gate set is actually not universal for quantum computation. And in fact, something even stronger is true. It turns out that you can actually efficiently simulate on a classical computer the evolution of any quantum circuit composed entirely of Clifford gates. But despite this, as I mentioned before, this Clifford group finds numerous applications in quantum information, which can largely be attributed to the very nice algebraic structure of this gate set. And we see that the set of Clifford gates, for example, it shows up in constructing error-correcting quantum codes and fault tolerance, in building efficient T designs, and also in some of the learning algorithms we saw for shadow tomography. So what is this algebraic structure that makes the Clifford group so nice? Well, one way of explaining it is that the set of outputs that you can get by applying a Clifford circuit to the L0 state is precisely the set of stabilizer states. And again, presumably many of you have heard about stabilizer states before, but for those of you who haven't, we start by defining the Pauli matrices, which are just these single qubit matrices, I, X, Y, and Z. And we define the n-qubit Pauli group as the set of all tensor products of these matrices on n qubits, along with arbitrary ±1 or ±I phases. And then a stabilizer state is just a state with the property that it is stabilized by exactly 2 to the n different Pauli matrices, where we say that a state is stabilized by some operator p. That just means that psi is a +1 eigenstate of p. And actually, it will be convenient to introduce this notation, because we're going to use it a lot throughout this talk. You can actually define, not just for a stabilizer state, but for an arbitrary state, its stabilizer group as the group of Pauli operators, because it's closed under multiplication, that stabilize that state. And I will denote this by stab of ket psi. Good. So as I mentioned at the start of this talk, one of the nice properties of stabilizer states is that they are efficiently learnable. So there is actually a polynomial time algorithm that, given copies of a stabilizer state, can uniquely recover the state with high probability. And this is due to the work of, I guess, first observed by Aaronson and Gottesman, and later in a slightly different algorithm by Montanaro. And the idea of these two algorithms is actually very similar. They both, at a very high level, they involve basically sampling uniformly random elements of the stabilizer group, and then repeating this until you get a full set of generators for this group, which is enough to determine the state. And one question that has gotten some attention in the last few years is whether there's any sense in which we can generalize this algorithm to more general classes of states. And in particular, this question has kind of been explored partially in works by Liang Cheng, and also Arunachalam, Bravyi, Dutt, and Yoder, both in 22, where they note that in quantum information, there is a wide class of, there's actually many different classes of quantum states that generalize the set of stabilizer states. And it's sort of natural to ask whether any of these generalizations also admit efficient learning algorithms.
There's something missing. You can sample from the stabilizers of the state. Don't you know the state already?
So like it's saying, from copies of the state, there is a measurement you can perform that will sample a uniformly random element. And that's how you use it to learn the state. Yeah. Any more questions? Yes.
Do these use coherent measurements or single copies?
Good. So the original algorithm of Aaronson and Gottesman only uses one copy of the state at a time. Montanaro's algorithm uses 2 copies of the state at a time.
I mean, I think we noted that you can get by with fewer copies if you make coherent measurements.
Right, that's true. So the sample complexity of Montanaro's algorithm is better. Good. So in this work, we're at least going to look at a couple of these measures of states that kind of generalize the set of stabilizer states, in particular Clifford+T states and states that have bounded stabilizer fidelity. And I'm going to tell you what these mean, starting with Clifford+T states. So I mentioned at the start of this talk that if you take the set of Clifford gates, this is not a universal gate set. But it is actually well known that it is almost universal in the sense that if you append any single qubit gate to this gate set that is not a Clifford gate, the result is a gate set that is in fact universal for quantum computation. A common choice of the gate that is added to this gate set is the T gate, which is this diagonal gate that just adds a phase of e to the I pi over 4 to the Ket1 state, which is chosen both, sometimes just for, I guess, notational elegance, but also in many cases mathematical convenience. And one thing that kind of has cropped up again and again in quantum information in regards to these kinds of Clifford+T gate sets is that there are a variety of different quantum algorithms and protocols in which there is a sense in which the the Clifford gates are cheap, and it is the non-Clifford gates that are kind of the limited resource that you really want to minimize. And this happens, for instance, in quantum error correction, where for a wide class of codes known as stabilizer codes, the set of stabilizer gates are much easier to implement on logical encoded qubits because you can implement them transversely. And for similar reasons in magic state distillation, where basically you often kind of assume that you can apply these Clifford gates basically for free, and then you just want to minimize the number of non-Clifford gates in your circuit. And finally, like another interesting something else that kind of demonstrates this idea is these classical near Clifford simulation algorithms, which what they do is they can simulate a circuit that is dominated by Clifford gates, and they usually have a runtime that scales polynomially in the number of Clifford gates and then exponentially in the number of non-Clifford gates. So as long as the number of non-Clifford gates is small, you still get an efficient classical simulation algorithm. And kind of the natural question that this raises for quantum state learning is whether something similar happens for learning quantum states. So if you have the output of a circuit that is composed mostly of Clifford gates, but then just has a handful of T gates, a natural question is, can you learn that state in polynomial time? And the first result that I will talk about is exactly a positive answer to that question. So we show that if you have a quantum state that is the output of a Clifford+T circuit that has n qubits and at most k T gates, then you can actually learn that state in time that scales polynomially in n and exponentially in the number of T gates. And I should mention that actually at basically the same time, there were 2 simultaneous works that achieved similar results, one by Leone, Oliviero, and Hama, and one by Hungleiter and Gullens, which we actually heard a little bit about earlier this week in Dominic's talk.
And is the number of copies also polynomial in n and 2 to the k?
Yes. Yeah. The number of copies. Yeah. So time and samples, I should really say. Yeah. Another thing I should note is that I'm only going to be talking about like Clifford+T gates for simplicity, but actually pretty much all of our results still hold if you actually, in fact, all of our results still hold if you replace the T gate by arbitrary single qubit non-Clifford gates. Basically, all that changes is some factors of 2 get added. And sometimes that 2 is just a multiplicative constant. Sometimes it's a 2 and an exponent. But otherwise, anytime you see T gates, you can really think arbitrary non-Clifford gates. Good. So this implies that, in particular, if k is like, logarithmic in the number of qubits, then you can actually learn the state in polynomial time. But this is actually not the end of the story. So there's a sense in which this task does not immediately become hard when k exceeds log n, because what we can also show is that if you have the output of a Clifford+T circuit that has strictly less than n T gates, then while you can't learn an entire description of the state, you can at least do some weaker form of learning. In particular, you can distinguish the state from a random state in polynomial time. Or another way of saying this is that if you have a state that is output by a Clifford+T circuit with strictly less than n T gates, then that state cannot form a cryptographically, or that state, states of that form cannot form cryptographically secure pseudorandom ensembles. Good. Any questions about these results?
So it's totally possible that there's an algorithm that goes like poly n comma k, like that would be. Like it doesn't violate any.
So I will kind of talk about it on the next slide, but like in short, that would sort of imply that you had a polynomial time algorithm to just learn arbitrary quantum states output by circuits of size k. And we wouldn't expect that to be true. Like if like cryptography, like under plausible cryptography, that should be hard.
Question.
Yeah.
So when you say it can be distinguished from random, do you mean like outputs of random circuits of certain depths, or?
I just mean like Haar random states. So like you have a state which is promised to either be of this form, or it is promised to be a uniformly random state. Then you can distinguish those two cases with high probability. Yes.
Maybe you said this, but what do you mean by learn? Like, what's the?
Good. So in this first case here, learning just means doing complete tomography on the state. So you learn a classical description of the state that is epsilon close in total in trace distance.
What is the description? Because it needs to say.
Good. I guess we will see that later in the talk, but it does let you prepare the state efficiently. It is actually not a proper learner. So if the circuit that prepares the state is a Clifford+T circuit, the description you learn is not necessarily also a Clifford+T circuit with the same number of T gates.
But wouldn't that say to Robin's question that you can't do it in poly NK? You can't write down a state.
I don't see the relation.
Like you need to be able to write down a description.
Okay, but like if you have a state that has a polynomial size circuit. Yeah, I think in Robin's question, the barrier is just computational. Yeah, I mean, I should note, like, I think it follows from like shadow tomography that like information theoretically, these kinds of tasks are easy. If you just care about sample complexity, there are efficient algorithms. What's really the interesting part here is the computational complexity.
So what is the model like when you say that you have polynomial time and n and to decay?
Good.
You run this circuit as many times as you want? Or?
You just get copies of the output state. As many copies as you want. So these are actually the two results I'm going to focus on for the rest of the talk. There are a few other results that I don't think I really will have time to go into detail about, but I at least wanted to mention them because I think they're also interesting. And they mostly concern a different measure of the non-stabilizerness. So in this case, we look at if you have a state, then like how many non-Clifford gates do you need to prepare that state? But a different measure of non-stabilizerness that we looked at is the so-called stabilizer fidelity. And intuitively, that just measures like how close your state is to a stabilizer state. And we have some similar results where we can show that if you have a state with large stabilizer fidelity, you can distinguish it from random. You can sort of non-trivially estimate the stabilizer fidelity, and also, in some cases, if the fidelity is large enough, actually find the nearest stabilizer state. And then finally, for some of our results, it actually turns out that you can achieve the same things using only single copy measurements. So you only get access to one copy of the state at a time. You can't perform entangled measurements across different copies of the state.
Why did you choose stabilizer fidelity out of all the measures of non-stabilizerness?
Why did we choose it? I think it was because we were really trying to actually look at a different measure known as stabilizer extent. In fact, we were really trying to look at something known as stabilizer rank, because that was something that had been raised explicitly as a question. And this was like as close as we could get to that. I guess arguably the stabilizer fidelity is like not quite as well motivated as the Clifford+T circuits.
Again, stabilizer fidelity just means largest fidelity to any stabilizer state.
Exactly.
Well, that sounds natural enough.
Okay. Yeah, I thought so too. Okay. Any other questions?
Do we know if the models are tight?
That's my next slide. So we sort of have two kinds of results in this paper. One is like the weak learning that I talked about, which is just distinguishing from random, and the other is like full efficient learning. And we study both of these tasks with regard to two measures of non-stabilizerness. One is the T count, and one is the stabilizer fidelity. And at least in 3 of these boxes, so we have new non-trivial algorithms in all 4 of these boxes. And in 3 of these boxes, we can at least show that under plausible cryptographic assumptions, our results are basically tied up to polynomial factors.
What are the assumptions?
Good. So it's basically that there are like linear time constructible pseudorandom functions, quantum secure pseudorandom functions. I guess it's like admittedly not the most well-studied assumption, but it's like definitely a barrier. Like it's basically saying like if you could improve any of these results, like the reason wouldn't be because you're really doing better on learning near stabilizer states. It's just you're learning like arbitrary outputs of quantum circuits better than brute force. Yeah. Any other questions about this? Okay, good. That about sums up everything I wanted to say about the results. In the rest of this talk, like I said, I'll mostly be focusing on the proof of the results in this second column concerning the T count.
So basically, efficient learnability you only get when you have a large overlap with some stabilizer state. Squared pi over 8 overlap.
Sorry, you're talking about this box?
Yes, it's possible.
For stabilizer fidelity. That's the only case in which we can show it's efficient. It's plausible that if you have like 1 over poly fidelity, that
That it would work even then.
yeah.
And so the algorithm is agnostic. Oh, we're meaning.
Yeah. Okay. So it's like technically not full learning of the quantum state. It's what we call agnostic learning, which just means basically output any stabilizer state that has at least that fidelity.
I see. Which might not be the true one, but. But there.
Well, actually, okay. So this is exactly the threshold
Yeah, right.
at which there
where
is
it
a unique.
I was about to say that.
Yeah. Yeah.
It looked like it.
Yeah. So maybe calling this agnostic learning is.
So then why,
Yeah.
I think, it might start out agnostic, but then it proves that its stabilizer God exists.
Yeah.
But agnostic just means that your state is not promised to be a stabilizer state, right?
Right. Like you're basically saying like find me the closest example from this concept class, where the concept class is the class of stabilizer states. Yeah. And it's saying like as long as you're sufficiently close, you can do that efficiently. I think maybe my single favorite open problem from this work is whether you can like push this below that threshold, and in particular to just if you have like inverse polynomial fidelity.
Mm-hmm. Yeah. So, good.
Any more questions?
So are these lower bounds, do they come from actually like learning classical circuits or like the you need them to be about quantum steps?
I mean, so again, they're just like they're pretty much all from pseudorandom functions. So it's just like if you have, which I guess are in a sense just classical circuits. Yeah. So it's like saying if you have an ensemble of pseudorandom functions that you can compute by linear sized classical circuits, but that cannot be distinguished from random by exponential time quantum algorithms, then these are basically tight. But I guess actually maybe we really only need that you have like linear time pseudorandom states. Yeah.
So when you say that these results are cryptographically typed, do you mean that, for instance, if you have more than log n t's, then there is no hope of having an efficient learner?
Exactly. Like if you could learn states that have more than log n t gates in polynomial time, then like that would that would imply, a new breakthrough in cryptography, basically. Okay. Any more questions about the results? Okay, good. So before I actually dive into telling you about the proof techniques, I want to take a step back and give you a bit of a Zen outlook about the math of this paper. And presumably, most of you either know exactly what the slide is about or have no idea what this slide is about. And what this is about is an analogy for solving math problems that was suggested by Alexander Grothendieck, who is depicted down here. And he suggested that if you think of the mathematical problem you're trying to solve as like a nut that you are trying to open, then there are two different approaches by which you can try to open that nut. The first is just a very direct approach. You hit it with a blunt object like a hammer until it starts to crack, and eventually by making enough firm blows, the nut will finally be opened. And this kind of brute force attack is what he described as being the approach of mathematicians like Jean-Pierre Serre, who is depicted up here. But Grothendieck himself advocated for a more indirect approach, which is, rather than trying to directly open the nut using brute force, you just let the nuts soak in some softening liquid like water, and you let them soak and soak and soak for as long as it takes for the skin to soften. And eventually, through basically no effort of your own, other than maybe occasionally rubbing the surface of the nut will open itself to you. And this is the approach to mathematics that Grothendieck advocated for. So why am I drawing upon this analogy? Well, I very much take the view that this is kind of the approach that our algorithms take, because what you will basically see is that we develop a bunch of theory surrounding the algebraic structure of these Clifford+T states. But then once we've kind of developed enough algebraic structure, the algorithms just fall out. And I actually also think this analogy is appropriate because if I look back on how we came upon these results, I think it's fair to say that it was kind of accidental. We were really just trying to understand the structure of these Clifford+T states, and then we realized that you can get these algorithms from it. So that's the high-level overview of what is to come. Okay. Oh yeah.
I'm not sure if somebody asked this before, but if you wanted to distinguish not between plus n-t gates and random, which is basically probably I don't know how many t gates, exponentially many. If you wanted to distinguish this between n and say more than 2n or more than something million, would that work?
So what do you assuming that the most efficient implementation is by some circuit of size with at most
so
n squared t
giving you a random circuit, a random state conditioned on.
Oh, a random. So that's different.
A random state conditioned on that it requires more than n squared t gates to less between n squared and 10 and n squared compared to this. Would you be able to distinguish?
I think if it's random circuits, then we should be able to. I might have to verify that. But I mean, you actually might answer that question already in the next couple of slides, I think. Yeah, because as we'll see, we'll actually kind of go through actually a different measure of how close your state is to a stabilizer state, which I think it holds for all states that have t count strictly less than n. But then I think if you have a random state that has t count larger than n, it would not have that property.
Right, so I guess one thing you're also saying is that I see n is the number of qubits, right?
N is the number of qubits.
So yeah.
There is also one other caveat here, which is that here the cryptographic tightness is only up to constants. So it's we can show that if you have less than n t gates, it's easy, and if you have more than I don't know, c times n t gates, it's hard. Technically, in that intermediate regime, you don't know anything. Okay. Good. So we're kind of just going to start with a series of observations about these Clifford+T states, which will lead us directly to what we need to understand about them. And the first thing we will observe is that suppose we have some arbitrary state psi. It has some stabilizer group. And we come along and we apply a gate U to this state psi. So what happens? Well, imagine, just for a moment, that an element of this stabilizer group that we'll call P actually commutes with the gate U that we apply. Then I claim that this same Pauli operator P is also in the stabilizer group of the state after we applied U. And the reason for this is very simple, just that if you look at P times U psi, you can commute P past U to get U times P of psi. And then since P stabilizes psi, that's just the same as U psi. And all of this is just saying that P still stabilizes U psi. So again, we're saying if the gate you applied commutes with an element of the stabilizer group, then that element is still in the post-gate stabilizer group. And to take an example, if we take the T gate, which is a diagonal gate, the T gate commutes with poly I and poly Z matrices. And as a result, you can show by, well, basically a simple inductive proof that if you have a state psi that is the output of some Clifford+T circuit with at most k many T gates, then the size of the stabilizer group of the state is at least 2 to the n minus k. For the intuitive reason that the T gate, it commutes with half of the poly operators. So each time you apply a T gate, you're at most cutting the size of the stabilizer group in half. Okay, does this make sense? So in some sense, understanding the structure of these Clifford+T circuits reduces to understanding the structure of these states that have, I guess, large stabilizer groups. So what can we say about these states? It turns out we can say a lot. In fact, these states have a very nice structure as captured by the following lemma. So imagine we have a state that has a stabilizer group of size 2 to the n minus k. So for example, if it's the output of a Clifford+T circuit with like k many T gates, then you can always find a Clifford circuit that sort of compresses out all of the non-Cliffordness of the state into k qubits. So in particular, there exists a Clifford circuit C that you can apply to psi, such that the result is just the 0 state on n minus k qubits tensor some arbitrary state on k qubits. So these states that have large stabilizer groups have this very clean structure. And not only that, you can also compute this Clifford circuit C efficiently given the stabilizer group of psi. I should note that I'm pretty sure we are not the first people to observe something like this. In fact, I believe this is basically a restatement of the fact that stabilizer codes can be encoded and decoded using Clifford circuits. But we also do care about the computational efficiency here of finding this Clifford circuit.
When you say efficiency, is that on the size of the stabilizer set, or is that on n?
It means given a set of generators for that stabilizer group, because there always exists one of size at most n, you can compute this Clifford circuit in time polynomial in n.
Right, so it's on over the generator, the number of.
Exactly. It's given a succinct description for the stabilizer group. Because otherwise it would be exponentially.
Basically, all the T-ness, all the non-stabilizerness gets compressed into phi.
Exactly.
Yeah. Can you also say something about Ket phi? Is it just T states tensor k times?
Good. So that's I don't know how to say something about that, and that's kind of exactly the reason why we don't have a proper learning algorithm. But I do get the sense that if you could say something about that state, then you probably might get more proper learning algorithms for these classes of states.
What could you hope, like, what's the best case scenario? That's like literally the T state, like T acting on ket 0, for example.
I guess that would be pretty nice. Yeah.
T acting on ket 0 does nothing. Right?
Oh, sorry, T acting on ket plus. Right. The state from which you can do.
Yeah, like the T magic state. Yeah. Okay. So yeah, these states that have a large stabilizer group, which again are a superset of the states that are outputs of Clifford+T circuits, have this nice structure. And basically the conclusion of this is that all of our results just reduce to learning the stabilizer group of an unknown quantum state. Because if you want to learn the state, then I claim that once you have learned the stabilizer group, you can compute this decomposition and then just run tomography on this quantum state phi, which will take like 2 to the k time, which is what we want. And similarly for like our pseudorandomness result, I guess there it's even simpler because as soon as you identify that psi is stabilized by any list of Pauli matrices, that is sufficient to distinguish it from a hard random state, because a hard random state is with overwhelming probability far from any state with that property.
By the stabilizer group, you mean the Pauli stabilizer group?
Exactly. Yeah. Yeah. That's how we define stable. Yeah.
So with this state phi, I don't think you can really say much about it, because an extreme case would be when this original state psi is just completely arbitrary.
That's true. Yeah. So if psi is an arbitrary state with this property, then phi can also be arbitrary. Yeah. That's true. But I guess the main question is that if psi is just a state that is the output of a Clifford+T circuit, does that apply any more structure on phi? And that I do not know the answer to. But I guess like this will also kind of be the sense in which like our algorithms may or may not be able to be improved. Yes, there's another question.
On the previous slide, you showed that with the number of T gates, the stabilizer has this number of Pauli stabilizers have a lower bound. I'm slightly confused. Can't you find? Isn't it possible for the T gates to be placed on specific qubits? Kills more of the stabilizer group?
Good. So when you apply a T gate to a single qubit, it can only kill the stabilizers that are like non-identity or Z on that qubit. But I basically claim that like because the set of stabilizers of some state is a group, that set like has to be at least half of the size. I see. At least half of all stabilizers.
I see.
Yeah. So again, in any stabilizer group, at least half of the stabilizers restricted to any one qubit have to be either the identity or Z. And by the way, this is also where the extra factor of 2 comes in if you allow non-T gates, because what happens is then arbitrary gate will just commute with I, and so there, instead of being reduced by a factor of 2, you will be reduced by a factor of 4. Okay. Any other questions? Good. So, like I said, really, in some sense now, our entire goal is just, given an unknown state psi, how do you learn its stabilizer group efficiently? And the way we're going to do that is by analyzing this function here, which I claim has a lot of nice properties. So what is this function? So for a Pauli operator W, that's just a tensor product of I, X, Y, and Z's, you'll define this function P psi of W for any pure state psi as just the squared expectation of this Pauli operator W times this normalization factor of 1 over 2 to the n. Okay, so I've defined this. What's so nice about this function? The first thing is that I claim that this function is actually a distribution. In other words, if you look at the values over the set of Pauli operators, then they're all non-negative, and they sum to 1. The fact that they're non-negative is easy to see because there's a square. The fact that they sum to 1 is a little bit less trivial, but it's like a straightforward computation that's related to the fact that psi is assumed to be a normalized state. But I claim not only is this a distribution, but it actually has some further structure to it. In fact, we can almost sample from this distribution efficiently, given copies of psi. In particular, we can't quite sample from p psi itself, but we can sample from a closely related distribution that we denote by q psi. And this distribution q psi is the convolution of p psi with itself. And the operational interpretation of that convolution, that just means that you can think of q psi as taking 2 samples from p psi and then multiplying the results together. And actually, the way you do this is via a procedure known as Bell difference sampling. The details of which are not really going to be that important for this talk, but I guess if people want me to, I could define how this works. Or you could just look at Dominic's talk from earlier this week, where he talked all about Bell sampling. I think there was something else I wanted to, oh yeah. One other note that I want to make at this point is that from now on through the rest of the talk, anytime I work with Pauli operators, I'm really going to actually be working with those Pauli operators modulo a sign. And this kind of actually only makes things easier. But if I really wanted to be proper about this, I would have to introduce some different notation, which I really don't want to do. So instead, I'm just going to kind of use Pauli operators, but with the understanding that I don't care about the phase information on those Pauli operators. Okay, so we have this function p psi. It's a distribution, and we can sample from something that's pretty closely related to it. Yes.
Why doesn't Bell sampling sample from p psi?
Good. So what happens is that Bell sampling in the Fourier basis will sample from p psi plus a shift, and you sort of need to take a convolution in order to cancel out that shift. I mean, I guess that doesn't really explain why. The real why is you have to do a calculation, see that there's just this extra term, but somehow that term cancels once you take the convolution. Good. So there's actually one other property of p psi that we use that is arguably really the key lemma that makes all of our algorithms work. And it is the following, that is this actually really nice duality property of this function p psi on subgroups of the Pauli group. And it says the following. Suppose you have a subgroup G of the Pauli group, which again, I'm going to be thinking of as a group modulo sign. So I'm just, completely ignoring the phase information of this group. If you look at the total mass that this probability distribution places on this subgroup G, then it is exactly proportional to the mass that this function p psi places on a closely related subgroup, actually a dual subgroup that I will denote by G perp, up to some constant of proportionality that depends on the size of G. And yeah, so in other words, it's saying that for any subgroup, there's some dual subgroup where the mass that p psi places on G is exactly proportional to the mass it places on that dual subgroup.
So in particular, if G and G perp both have order 2 to the n, right? Then it's an exact equality.
Yes. Yes. So what is this subgroup G perp? It turns out this subgroup G perp is exactly the commutant of G. So in other words, it is the set of Pauli operators P such that P commutes with every element of G. And this actually really is a dual subgroup. So you can basically verify that if you take the dual, if you take the commutant of a Pauli subgroup, you just get back your original subgroup G. Good. So somehow the mass that p psi places on a group G is related to the mass that it places on the commutant of G. So why is this useful? So let's think about what happens when we plug in G to be the stabilizer group of psi. So again, this is just the set of Pauli operators of which psi is a +1 eigenstate. And because of how p psi is defined, if we sum over all w's in G of 1/2 to the n times psi w psi squared, since psi w psi is 1 because w stabilizes psi, this is just the size of g over 2 to the n. And so if we plug that into this equation, the left-hand side is g over 2 to the n. So the conclusion of this is that this function p psi, the sum over the dual subgroup is exactly 1. Or another way of saying this is that if g is the stabilizer group of psi, then all of the mass of this probability distribution is on the commutant of that group. So in other words, every time you take a sample from p psi, the sampled Pauli operator will commute with every element of the stabilizer group of psi. Yes?
How are they sizes related, the G and G perp? They multiply to 2 to the n?
They multiply to 4 to the n. Yeah. Yeah, so if it's like if G has size 2 to the n, then G perp also has size 2 to the n. Any other questions about that? Yeah, so this is really the key property that the sampled Pauli operators always commute with the stabilizer group. And in fact, there's actually also like a robust version of this that holds. This requires just a little bit more effort, but you can sort of show conversely that if you can find a subgroup G perp that accounts for a large fraction of the p psi mass, like a 1 minus epsilon fraction, then in fact psi is basically epsilon close to some state that actually does have G as the stabilizer group. And this is really the key property that we use, because we basically say that, like what this basically implies, is that if you take enough samples from this distribution p psi, then eventually you will have like a very good proxy for the stabilizer group of G. And indeed, actually, believe it or not, we have already developed pretty much all of the algebraic tools that we need. I can already start stating the algorithms that we have, starting with our pseudorandomness distinguisher. So again, this algorithm, it takes a state psi, and you're promised that either the stabilizer group of psi is non-trivial. So for example, psi is generated with strictly less than n t gates, or psi is just a Haar-random n-qubit state. And the following algorithm distinguishes these two cases as follows. So you just sample a bunch of Pauli operators from this distribution q psi, which, as I mentioned, is not exactly p psi, but it's like close enough that the math works out. You just take a linear number of these samples, and you let G be the dual subgroup, the commutant of the group generated by these samples. And then you just accept or reject, depending on whether the size of this group is greater than 1 or not. Yes?
About this random thing. I mean, isn't your algorithm much stronger? Why isn't your algorithm much stronger?
It is. It's on the next slide. But I wanted to start with the easy case. And this case is, so the reason this case is easy, so if psi has a non-trivial stabilizer group, then it's very easy to show, by this duality property here, that all of the sampled operators will commute with all of the elements of G, so that when you take G to be the commutant of the sampled operators, you always get something non-trivial. But conversely, it's pretty easy to show. You can show it using this robustness property, but also just by like a direct calculation, that if you take samples from this distribution for a Haar-random state, then with overwhelming probability, you will, the samples will not commute with anything other than the identity, and so you will, with overwhelming probability, reject. But as Dorit pointed out, in fact, we can actually do something even stronger than this. So in fact, we also have an algorithm that basically property tests the size of the stabilizer group of psi. So in particular, if you have a quantum state psi with the property that either psi is stabilized by some group of Pauli operators of size at least 2 to the n minus k, or it is epsilon far from that, then you can distinguish these two cases using essentially the same algorithm. So there's some dependence on epsilon in the number of samples, but otherwise it's still just you sample a linear number of times from this distribution. You compute the commutant of the group generated by those samples, And then you just accept or reject depending on whether the size of that group is bigger or smaller than what you expected. And once again, like the way you prove this is using this robustness property that eventually by sampling enough times from this distribution, you will with overwhelming probability find a subspace that accounts for a large fraction of the p psi mass. And then by taking the commutant, you can sort of be confident that that commutant, this resulting subgroup G, approximately stabilizes psi. And then finally, we have our state learning algorithm, where you basically just add on this one extra step of using this kind of Clifford decoder to actually learn the state. So once again, the algorithm just takes the form of you sample a linear number of times. You let G be the commutant of that of those samples. You use G to find a Clifford circuit that approximately maps psi to a state of the form, just a tensor product of zeros and some k-qubit state. And then finally, you run tomography on phi. And promise that you're given a state that has a stabilizer group of size at least 2 to the n minus k. You approximately learn psi to within some error epsilon. So that's basically all the algorithms. Are there any questions about this? I thought I had something else to say.
So these are multiple copy.
Yes. Yeah, this does use multiple copy measurements. It actually uses like only 2 copies of the state at a time to do this Bell sampling. But actually for this algorithm, so this is something we're working on now, you actually can do, you can achieve a similar learning algorithm using only single copy measurements.
And it's still computationally efficient.
It's still computationally efficient. But I think for these other algorithms, I suspect this becomes impossible. That might even be proven, actually. At least in the case where you only have like this promise that the stabilizer group is either large or not. Yeah. Another question?
Do you have a sense for how strong the promise is?
What do you mean?
In the sense that if I have some Clifford+T circuit, will it always satisfy this promise?
Like the yes case? Yeah. Well, so if it's a Clifford+T circuit with at most KT gates, it will always satisfy the yes case. But with more than that, then, who knows?
Sorry, why do you think it breaks if you have the single copies that you mentioned before? Like if you learn it, then you can do flat tests, right? Or some people.
So the problem is I don't know that you can learn the entire stabilizer group efficiently with single copy measurements.
Oh, okay.
So like here, it's sort of okay because the tomography algorithm takes time that's like 2 to the k. And the single copy algorithm also takes time that's like 2 to the k to learn the stabilizer group. But for this, the point is you're like learning the stabilizer group in polynomial time, regardless of the size. And that's the thing that I think is hard. Yeah, because like, I mean, I don't know if it's literally been shown, but like there were these results showing that like if you want to learn the expectation of like some Pauli observable of an unknown quantum state, then like this is exponentially harder using single copy measurements than 2 copy measurements. And like I feel like something similar has to hold here as well. Okay, so that about summarizes how the algorithms work. Just to briefly recap, we give new algorithms for learning these Clifford+T states and other states that generalize the stabilizer group. I think what's quite remarkable about these algorithms is how operationally simple they are. Really all the work is just in the analysis, but the algorithms themselves are quite simple. And I think the main take-home message is that even for these states that generalize stabilizer states, the algebraic structure of stabilizers and polymatrices is very powerful. And I think I will leave you with that. So thank you.
Questions?
You said getting polynomial sample complexity for all these questions is just straightforward. The time complexity part is the hard part. In these straightforward algorithm that gives you polynomial sample complexity, can you also do it one copy at a time, or those algorithms?
Yes, yeah, because it's just like classical shadows protocol. So in fact, the measurements you do are literally just random Clifford measurements.
It's a straightforward conditional on the classical shadows paper.
Yes, the classical shadows paper is not that trivial.
Yeah, okay, fine.
So when you brought the generators earlier, you track them all with these things to show up first.
Sorry, like what do you mean? Like in this algorithm or this algorithm?
Well, we should expect to know what the generators are. I'm sort of trying to understand if your approach to your asset is from that principal algorithm because of the relation to the one that
Okay, I don't know what a lot of that means, but I mean, like we do, store the generators of these stabilizer groups. Like, I don't know if that directly answers your question. I mean, this was also related to something else someone asked earlier, which is that we store these stabilizer groups in like a succinct fashion. Like you just store the generators. Storing the entire stabilizer group would require like exponential space. But, yes.
Is your single copy measurement learning algorithm, is that also single qubit?
No, it's like random. It's like it's only Clifford measurements, I believe. We just like apply a Clifford and then measure. It's not just single qubit.
Anyone else?
Actually, I have a question, which is like, does anyone know if like someone has proved something like this before? Because I feel like there's no way that we are like literally the first people to observe this. So, like, it's just like a very nice algebraic property. It's like related. There's like I think an equivalent fact, which is that this function p psi is like, it's its own Fourier transform when you define the Fourier transform appropriately.
It's like Poisson summation formula.
The what?
Poisson summation.
Oh.
I'm sure there are previous lemmas that show that one thing equals another thing.
Yeah.
I don't know if this is a relevant observation, because it looks a lot like the probability of winning a non-local game in which you're playing with the stabilizers of the state psi.
Mm.
So in that sense, what you show looks a bit like rigidity for that.
Oh, like this thing?
Yeah.
Yeah, it could be. I mean, fundamentally, that's basically just like a statement about representation theory, right? So maybe something similar is going on here.
It looks similar to saying that, like, if your state has like more than one instance on the base, then has more than one bases.
Right. Yeah. I mean, it is. It is somehow using something about like the duality between.
I guess I would also ask the question, like, could you replace the group of Pauli matrices with some other group instead of
Sure.
like how much of this would carry through basically?
Yeah. I don't know.
I mean, I guess, the straightforward thing to do would be to insert qubits, have qubits that are how
Oh, sure. No, I think something like this does hold for qubits as well. Because like I said, I believe this is like equivalent to some Fourier transform property, and like this p psi of w. So like this was studied in a paper by Gross, Nizami, and Walter. And like you can define something similar for higher numbers of qubits. Yeah.
So once you have learned the state, like how hard it is to learn the actual circuit?
Good. I have no idea. I don't think I really know anything better than some kind of brute force. Like, I mean, okay, you can find some circuit that prepares that state phi. It will have size 2 to the k. So it's like an exponential blow up in the number of non-Clifford gates potentially. So, and I don't know anything that beats that. There was another question?
Can this be extended when you consider that someone's hardware factor is Clifford anti-gate?
Sorry, say that again.
Considering, can you extend this learning algorithm, including noise, after it's Clifford?
Oh, including noise. If it's just like single qubit depolarizing noise, for example, I don't believe so. In fact, I think I've even seen it claimed that like learning even stabilizer states is hard with depolarizing noise, like information theoretically. But I'm not certain about that. But I definitely know that these algorithms break.
It depends on how many layers of noise you have.
Right, yeah.
In general, you can expect like the output conversion maximally makes it
Yeah, right.
exponentially faster than the number of layers.
Yeah. But yeah, that's a good question. So these algorithms are very non-noise robust.
First, part of your algorithm where you're learning the stabilizer group is somehow on a high level very similar to Simon's algorithm, because they were also sampling a bunch of strings, and then you want to learn what's the span of all those strings.
Yeah. Yeah.
So you said with single copies and in time 2 to the k, you can learn the stabilizer group.
I believe so.
So with 2 copies, is it like even faster than, it doesn't depend on k? Or?
Yeah, with 2 copies, it's just this algorithm. So you learn like an approximation to the stabilizer group, right? It's like, okay, psi could be, arbitrarily close to some state that doesn't have, exactly that stabilizer group. Like this, I believe this algorithm is basically optimal.
And is it possible to say, like, super briefly how the single copy one?
Is it possible? So, I mean, it's morally similar. Like, so what happens is, okay, if you like take a random stabilizer state, if you take a stabilizer state and measure it in a random Clifford basis, there is some probability that the support of that state in the computational basis will be a proper affine subspace of all n-bit strings.
So the measurements are random Clifford measurements?
Well, it's like you pick a random Clifford, but then you have to measure like n times from it. So you pick a random Clifford, you measure however many times from that basis. And basically, if you see that you are in a proper affine subspace of f to the n, that tells you a generator of the stabilizer group. So this is actually basically the Aaronson and Gottesman algorithm for learning stabilizer states. In a way, we're just observing that you can kind of do the same thing, even if you have a state that's not a stabilizer state, but that has a non-trivial stabilizer group. But the problem is you need to take, like the number of samples you need to take before you find like a good Clifford, scales with like 2 to the k or something.
Anyone else? All right, well, thank you, William.
Thank you.